This video will focus on planar graphs. First of all, let's go through the terminology. A planar graph is a graph that can be drawn with no edges crossing over. So obviously the graph that we've got here is not planar. The reason for that is at this point here we've got these two edges crossing over at this exact point here. So that's not what we're after here, and we could quickly redraw this as planar if I remove this connection here. I can't just remove a connection, I've got to actually have this network diagram or this network graph is indicating that there's a connection between A and B, so I can remove it there and actually sweep the connection around the back. That still means that there's a connection between A and B, but now it meets the requirements of being planar, and that is that it's drawn with no edges crossing over and that it's connected. That loop could go any way you like, so I could actually get rid of this and I could loop it around that way. I could loop it back around this way if I wanted. So it can look as any way you like, and you've got a bit of artistic liberty. Okay, faces, also called regions. A face is the region outside a graph and also the enclosed regions inside the graph. So if this is a graph that you've got here, what the example's already doing it for us, it's showing us that there's 6 faces, and it's saying that this area outside here, this is all one face, and they've counted it as the 6th face. The first one is this one here, second is this one here, third, fourth, and fifth. So that's why this particular network graph has 6 faces. Euler's formula. Euler's formula basically holds true, or does hold true rather, for any graph that is connected and planar. And the formula is vertices plus faces subtract edges equals 2. Okay, I won't go on to prove that, but this network diagram is connected and planar, and it will meet the condition for Euler's formula. Let's actually put it into practice with the chapter examples. Okay, so it's asking us here to redraw the following networks as connected planar graphs, if possible. The issue with this first one is that we've got this crossover point here and this crossover point here. Okay, so what can I do? I can't remove this line because that will mean that I have to make a connection from E to G through these ones, which will actually make it non-planar again. So what I'll do is I'll remove this line from here, this edge from here, and connect D to H using that line there. I'll do the same thing here. On the opposite side, I'll remove this line, should be calling it an edge, and connecting it there. So now we have a planar connected graph that will meet the requirements of Euler. Okay, this here we have a crossover point here. The issue is though, imagine I remove that line there and just redraw it as AD. This is a non-connected graph, so we can't redraw this one as connected planar because it's disconnected. Okay, this particular graph here has 2 crossover points here. So many different answers to this one. I'll get rid of that line and make a loop, not a loop, an edge connecting G and B. And I'll do the same thing over here. I'll remove this line, this edge, and connect C and E. For example 2, what they want us to do with the graph is to show that Euler holds. That is, that that his formula is true in this case. Okay, so what we'll do is we'll just write down his formula. Vertices plus faces take away edges equals 2, and then go on to actually calculate this. So we've got 1, 2, 3, 4, 5, 6. The number of vertices is 6. The number of faces, well, we've got 1, 2, 3 enclosed areas plus this whole outside area, which is 4. The number of faces is 4. The number of edges, 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 edges, must equal 2. 6 plus 4 is 12. 6 plus 4 is 10. 10 take away 8 is 2. 2 equals 2. That's how I show that Euler holds. Compare the sum of the degrees of the vertices and the number of edges. Okay, so let's work out the degree of each vertex. I'll write each vertex down. A, B, C, D, E, and F. Okay, the degree of A is 2. The degree of B is 3. The degree of C is 3. The degree of D is 1, 2, 3, 4. The degree of E is 2. And the degree of F is also 2. Let's add those numbers together. 2, 5, 8, 12, 14, 16. The sum of the degrees of the vertices is 16. And what we want to do is compare that to the number of edges. The number of edges we counted earlier is 8. And what you'll find is, for any connected planar graph, is the number of edges multiplied by 2 will give you the sum of the degree of the vertices, or if you've got the sum of the degree of the vertices and you divide that by 2, that will give you the number of edges you have. Third question, how many odd vertices are there? This is an odd vertex. This is an odd vertex. There's 2 odd vertices. We've got some tests or some values for the pronumerals to test with Euler. Remember, his formula is V plus F take away E equals 2. So let's try it using these numbers. 7 plus 4 take away 8 equals 2. 7 plus 4 is 11, take away 8 is 2. 11 take away 8, 3 does not equal 2, so Euler doesn't hold for that one. Let's try it for this. Okay, now we'll do Euler on the last question. So we've got 7 plus 5 take away 10 equals 2. That's 12 take away 10 equals 2. 2 equals 2, and what that basically means is that Euler holds for that last particular question.